Adelson-Velsky and Landis tree. An Adelson-Velsky and Landis tree, or AVL tree, is a BST with a balance condition. This balance condition ensures that the worst depth of the tree is O of log n. An AVL tree ensures that for every node, the height of the left and right subtrees differ by at most 1. Let's have some trees. Is this an AVL tree? Is it balanced? Let's check. So first we check this subtree here. Is this subtree balanced? Well, yes, both of these nodes, or both of the children, have heights of 0. Now this one is obviously balanced because it doesn't have children. So does these two. So this subtree has a height of 1. This one has a height of 0. So this whole tree is balanced. So this is an AVL tree. Now how about this one? Let's check this subtree, because this subtree is just this one just flipped. So this whole subtree here is balanced. Now how about this one? Is this subtree balanced? So its left child is -1, has a height of -1. And this one has a height of 0. So this one is balanced. And the whole tree is also balanced because this one has a height of 1 and this one has a height of 2. Let's compute for the worst case height of AVL trees. Let's first ask the question, what is the worst scenario for AVL trees? This one is an example of a quote-unquote worst scenario. Now, why do you think is this an example of a worst case for AVL trees? Can you think of why? This tree is an example of an AVL tree of a certain height, let's call h, with the minimum number of nodes. If we look here, we could have rearranged some of the nodes and its height would be 1 less higher. For example, we could move the root here to this position as the left child of this node and make this one the new root. So doing that will still obey the AVL and BST properties. And that's it. That's the worst case for an AVL. So let's compute for that. Let n of h be the minimum number of nodes in an AVL of height h. Let's define n of h recursively. The value of n of h is minimum provided n of h minus 1 is minimum and n of h minus 2 is also minimum. Thus, n of h is equal to n of h minus 1 plus n of h minus 2 plus 1. To illustrate, the minimum number of nodes is 1, which is the root, plus the minimum number of nodes for the left subtree, this one here, and the right subtree. And as you can see, one subtree has a lower height, h minus 2, because we are allowed to have a difference of 1 in AVL trees. So again, we have n of h is equal to n of h minus 1 plus n of h minus 2 plus 1. To make simplifying easier, we'll replace the larger subtree with the smaller subtree. So now we'll have 2 of these. And then we ignore the 1, since we're getting the bound using asymptotic analysis anyway. So again, instead of doing this, we replace this one with the smaller subtree. That's here, n of h minus 2. So there will be 2 n of h minus 2's, like so, and then we ignore the 1. So now we have n of h is greater than 2 times n of h minus 2. If we expand this using the iteration method, we'll get this, and then this, and so on, which produces this pattern here. So when does the recursion stop? What is our base case? And what will be the value of I for it to stop? We stop iterating when we reach the smallest possible subtree, n of 0. And when that happens, I will be h over 2. Substituting h over 2 to I rather, we'll get 2 raised to h over 2 times n of h minus 2 times h over 2. Simplifying this, we'll get this. So that will be simply n of 0. And n of 0 is just equal to 1, since the minimum number of nodes of a subtree with height 0 is 1. Let's try to get h. So we log both sides, and we'll get this. Therefore, h is less than 2 times log of n of h, and therefore, our height is O of log n. Hence, an AVL tree with n internal nodes has height h is equal to O of log n.